I am recording. Okay, Brandon Thomas. Carlos Duque. Now, okay, good. Ricardo, wow. Omar. Daniela. Okay, okay. Okay. So now we start. I erase number 6. Now number 7. Well, number 7 is, you see, number 7 is evaluate one line integral, pero it's closed curve of the expression inside the integral is x squared dy, and the curve C is it's given graphically, no? Is the -1, +1, okay, in this direction, and also it's a semicircle in this direction, semicircle with the radius 1. Half upper unit circle, half, this is a straightforward, yes, for you. Okay, super. But in this case, they want doing by the green theorem, because I want to record green theorem. Green theorem say que one line integral in closed curve, mandatory to apply green theorem closed curve. This is dr, no ds. dr is equal double integral. This is double integral, and the region R, okay, obviously the region R in our example is this region. This is the region R. Entonces the integral function is the curve of the vector field. Entonces this case dA, que bueno, normal is dx dy or dy dx, or in polar. I suppose que we ending in polar because it's a circle, semicircle at least. Then we compute the curve first. Well, first of all, determine what is the vector field, because the problem say in the weird way, no, this is P and this is Q, I suppose, no. Entonces the vector field is obvious que es y squared, x squared. P component and Q component. Now determine the curve, que es super easy. Remember the curve in 2D is a scalar function, is qx minus py. Derivative q with respect to x is 2x. Minus derivative p with respect to y is 2y. Okay, 2x minus 2y. Okay, so now I set up the double integral in the region R. Integrand function is 2x minus 2y dA. To compute that, well, there are many ways. In my opinion, the best way is using polar, no? Because the region is, is a semicircle, no? If you convert to polar this integral, well, first of all, I need to write the integrand function using the variable of the polar, no? Que is x is r cosine, y is r sine theta. Because I replace 2r, this 2x is 2r cosine theta minus 2r sine theta. Remember Jacobian, r dr dθ. And the limit go in r from 0 to 1. So, right? Any point on the 0 to 1, from 0 to 1. And the middle one, we have intermediate value. And theta go from 0 to pi, not to pi, because it's not entirely secret, it's a semicircle. Okay. Well, you can separate Well, you can, for example, here, you factorization, y, no, r. We have 2 cosine theta minus 2 sine theta. In this case, the limit is a constant number, numerical, no variable. And the integrand function is totally separable. So we can integration, for example, with respect the theta separately to the r is 2 cosine theta minus 2 sine theta d theta. Multiplication by another integral go from 0 to 1. Okay, obviously is r squared dr, because we have one r here, another r de Jacobi together is r squared. Entonces that part is easy. This is r cubic divided by 3. Evaluating between 0 and 1. It's obvious it's 1/3. This part also is relatively easy. When you factor out 2 here, antiderivative cosine is sine. Evaluating between 0 and pi. Minus antiderivative sine is minus cosine, but we have a minus in the front, become positive. Evaluating between 0 and pi. That part is 0, it's obvious, no? Because sine pi is 0, sine 0 is 0. But that part no. Because cosine pi is -1. Es -1. And cosine 0 is +1. But okay, it's cosine. Let me write in detail. Wait, relax. It's cosine pi minus cosine 0. It's a -1, and this is +1, but we have a -1 in the front, is a -2. And -2 times 2. Sorry. A ver. It's okay. It's okay. -2 and all 2, we have a -4, no? A multiplication -4. Third. Let me check it, because in my paper, cosine pi is -1. Minus cosine 0, que es positive. Es -2. And -2 times +2 is -4. And -4 times 1 positive 1/3 is -4. Okay. Any question? Any question? Green theorem, application of the Green theorem to compute line integral. All good. Important. Must be closed curve. Si es open, no. Closed. Entonces now the you set out the double integral in the region bounded by the closed curve. Okay. Entonces all good. Hey, Jocelyn, all good? Brandon, answer me. Yes, no, complicated, easy. Okay. Let's move on to number 8 question. 8 question. The 8 question is, let's see, evaluate this again. But it's a weird format. It's xy multiplication dx plus dy. It's weird, very weird. So now I suppose you multiplication this and this and this and this. I have in the curve C. By the way, the curve C is the unit circle, no? Let me see. Yes, unit circle. Totally full unit circle, like that. 1, 1, -1, -1. Unit circle. This is my curve C. I suppose counterclockwise. So now my line integral is like xy dx plus xy dy in the cursive. Therefore, the vector field associated with this line integral is xy comma xy. No? It's a coincidence, que es the same. And of course, dr is dx dy vector. Dx first, dy secondly. In this format, this is P, this is Q. You apply one more time the problem say green, no? Green theorem. The green theorem, remember, we convert this line integral in double integral. In the region R, by the way, the region R is this. Is the this inside the unit circle. This. Because it's surface, no? Pero flat, surface flat, no curvy. Of the curve of the vector field, the dA. I put dA, not dx dy, because I don't know if I ending in polar or suppose, of course, I ending in polar because it's circle. To the curve f, the formula is qx minus py. Okay, this is p, this is q. And you differentiate partial derivative of the q with respect to the x is y. Partial derivative of the p with respect to y is x. This is the curve. But our double integral can allow us to compute the line integral using the green theorem, a double integral in the region R, integral function is y minus x dA. Boom. So you convert to polar, so we have r sine theta minus x is r cosine theta. The Jacobian is r dr theta. And it's a unit circle. This is a unit circle vary from 0 to 1 and 0 to pi. This is very, very similar. We can separate into integral from 0 to pi of the sine theta minus cosine theta d theta multiplication. So, are you aware that this situation is possible doing when we have a limited constant and also the integrand function is totally separable? This is r squared dr, because this r and this r together multiplied by this is r squared from 0 to 1. Okay, this is similar. This is the answer we did before. This is 1/3. But this no. This no, because the antiderivative sign is minus cosine theta. Evaluating between 0 and 2 pi. And the antiderivative cosine is sine. And this stays the same negative. Sine theta evaluating between 0 and 2 pi. This is, let me see, 2 pi. This is negative 2 pi, cosine 2 pi is 1, no? And this is cosine 0 is 1, 1 minus 1 is 0. It doesn't matter if you have a negative here. This is 0. This guy is 0. It's 0, no? And this is 0 also because, look at that. Sine 2 pi is 0, sine 0 is 0. It's 0. 0 times 1/3 is 0. The final answer in this problem is 0. Okay. Any question? Okay, this was the answer of the question number 8, no? Number 8. Okay, that was number 8. Everyone have the doubt, question? No. This is a moment, you know, because this is a review package, you know. Shahir, Heidi, Everything okay? Jocelyn, Brandon Thomas, Carlos Duque, Ricardo, Omar. Okay, good. Okay, it's easy. Okay, let's go number 9. Number 9 is the application of area. So we need to compute the area, no? Find the area of the enclosed curve. O sea, okay, number 9. Number 9 is given a curve que es expressed like a vector value function, no? It's a curve because we have only one parameter, es t. It's cosine square t, comma, cosine t sine t. Cosine t times sine t. And t vary from 0 to pi. 0 pi. So the interval, the domain of t is from 0 to 1 pi. So we study when you study the Green theorem, que one application is compute the area. And you know que area is maybe the double integral when you consider que the integral function is 1. However, they are equivalents using the Green theorem, using line integral. So instead of doing by the traditional way, que es double integral, no, we are doing like a line integral because they are equivalences. And this is a closed curve, of course. Entonces es the formula que you need to remember is only 1/2 integral in the closed curve x dy minus y dx. This is the formula. The formula que allows us conversion double integral when the integral function is 1 to the line integral. Okay, so x, in the parametric, this guy is x, this guy is y, no? So x is equal cosine square. And y is cosine t sine t. Entonces I determine dy and dx. Differentiation que es super easy. That dx is equal. Deriva de cosine square is using chain rule is 2 cosine t, and deriva de cosine is minus sine. I put the minus here at the front, sine t. Likewise, deriva this. Well, deriva this is more complicated because I'm using the product rule, no? Deriva the cosine is minus sine. Multiplication by sine, this is sine square. Plus deriva the sine, que es cosine. Multiplication by cosine again. Wow, cosine t. And this is no one because it's minus. Okay, now this is dt here. Okay, entonces I set out the line integral 1/2 integral from 0 to pi, because I do when I do the parameterization, we can convert the line integral to regular integral like a calculus. So you put cosine t, cosine square t, que es x. I do step by step. Multiplication by dy, que es minus sine square t plus cosine square t dt minus, I am here, this minus is this minus. Y is cosine t sine t multiplication something. Multiplication by minus 2 cosine t sine t dt. Well, so this is a long algebra, but okay, let's do it. This is when you apply distributive property here. We have minus sine square t cosine square t plus cosine to the 4th power t. And when you multiply this and this, we have positive, positive, positive 2, positive 2, positive 2 cosine square t, sine square t, dt. This is the, I omit the integral because I manipulate algebraically the integrand functions expression inside the integral. I can see, wow, look at that. I see okay, this is lighter, so 2 minus 1 is 1. So actually we have cosine 4 power t plus cosine square t sine square t. And why not? You factor out cosine square t outside. And we have cosine square t plus sine square t. Wow, this is actually S1. Therefore, this big expression I can manipulate and condense in only one cosine square. Actually, my problem so far is 1/2 integral from 0 to pi of the cosine square t. Okay, this is super easy. This is the classical problem Cal 2. You using the half angle formula. 1/2 integral from 0 to pi. Half angle formula say, let me copy here, cosine square t is equal 1 plus cosine 2t divided by 2. So we have 1 plus cosine 2t divided by 2. This 2 is a constant dt, don't forget dt. This is a constant, it's 1/4, 1/4. And we have two integral. One integral from 0 to pi of the dt, no? dt times 1, no? Plus another case from 0 to pi cosine 2t dt. This is the situation that we have so far. But wait a sec. Okay, good. Yes. Well, okay, this integral es obvio que es 0. Bueno, integral cosine es sine, evalué en pi y evalué en 0. Both guys are 0. Sine pi is 0, this is 0. This no. Then I said this is pi. Pi minus 0. So integral dt es t, evalué en between pi and 0 es pi. This guy is pi. Entonces, ¿cuál es the final answer? Pi over 4. Oh, this is the area of this figure. Okay, by the way, I don't know. This looks like circle, maybe. Circle where the radio is a circle. Yeah, it's a circle. This is a circle, so we can use in maybe Desmo or GeoGebra to graph this parametric function. It's a circle. It's a circle, but the circle, the center is not in the origin. It's in another place, but it's the same. The radio is, let me see, the radio is 1/2. When you square in 1/4, pi, perfect. Okay, so I did the graphic of this in in parametry. I like so much Desmos, and the graph look like that. Look. It's a circle. This is at t equals 0. This is at t equal pi over 4. This is at t equal pi over 2. This is at t equal 3 pi over 4. And rotate in that direction. And this is the area. Okay, try to looking for. Look, this area. The center here is 1/2, 0. Therefore, the radio is also 1/2. Using the elementary formula for the area for the circle is pi radius squared. 1/2 squared 1/4. You get the same answer. Okay. Any question? Number 9. Easy, easy or complicated, complicated? Easy, easy. Okay. This to me. Duque. Good, Duque. Okay, guys. This is the beauty of the education. No? Education is a process. Okay, little by little. I need to push you. I press you. But little by little you learn. Definitely. Repetition. It's important. That's the reason que you see I always doing the review package, big review package before the test. No? And the test is very, very similar, no? Number 10. Number 10 is more complicated. Okay, in number 10, we calculate the surface area. The surface area is surface integral when the surface area, what is the formula? It's the surface integral when the integrand function is 1. Yes. Es el surface integral pero escalar, no flux. When the function f, x, z is 1. Entonces we compute the surface area. But it's easy because the surface, I need to compute the surface area is given like a vector value function. In this case, using the general UB variable. Remember, sometimes in some case, when you are doing the parameterization of the surface and you apply one specific coordinate, x, y, or r theta, because you apply cylindrical or spherical, que phi and theta. But in this case, general, like in curve, the parameterization you call T, well, in this case, in general, I call UB. Okay, it's given by U cosine B, comma U sine B, comma U squared. And of course, given the domain of the variable UB is in between, U is between 0 and 1, and B is in between 0 to pi. So you are doing the graphic of this. Okay, we are doing always. This is, for example, B, U, doesn't matter. The order is a plane. This is 0 to pi, and 0 to 1. So this is our domain of the parameterization, 2 parameter. And when you ending the surface integral and you convert to the double integral, this double integral you are doing in this region. By the way, guys, using intuitive idea, intuition, no mathematics now, intuition. This parameter surface, what do you think? Using your common sense, imagination, what do you think? What kind of surface you very well know represent? Okay, suppose you are not having to identification surface and parametric. This is a little bit weird for you, I understand. However, using intuition, okay, what do you think? What kind of surface it is? U cosine B, comma, U sine B, comma, U squared. What do you think? Circle, no. Gerardo dice circle, no, wrong. Circle is no surface. When you see circle, maybe you say disc. Because circle is the circumference, circle. However, the surface is a surface, no? It's no curve, it's surface. So maybe you say this, tan, pero no, it's not this. It's not this. It's another thing. Marco, David, Fitby, Daniela, Omar. I appreciate so much you try to identification this survey, guy. Come on, come on, come on, come on. You have no idea. What is the glue? What is the glue? What is the glue? Look, look. The radio is not constant, no? The radio is not constant. It's a variable. Maybe you are right, Gerardo. It's a this, like that. Shh, because the radio is not constant. But the identification is because the Z component, is the last one, the third one, is square. Yes or no? When you're moving on the Z-axis, the component increasing, but it's square, no linear. Exactly. Very well. Ese paraboloide, like that. Ese paraboloide. Ese paraboloide. No, no con. Con es linear. Paraboloide es parábola, no paraboloide. Okay. This is a paraboloid. And you can see, yeah, of course, you can see you open Desmos, no? GeoGebra, sorry. And you put like that, like a surface command, no? You put surface. And of course, you doing that when the class is over, no? And you put u cosine b, coma, u sine b. Es obvio que that part alone, suppose que I put it here, is this, no? But the C component is u squared. So u vary from 0 to 1, and b vary from 0 to pi. You put this in GeoGebra, you see the paraboloid. You see the paraboloid. Paraboloid que es obvio que es along the z-axis because the part is square, and open up because positive the parabola. Okay, so what should I do? Well, you apply the formula. You take the vector value function in 2 dimensions, differentiate with respect to u. Let's do it. Derivative with respect to u is super easy. The derivative this is cosine b only, comma, sine b, because you consider b constant, and 2u. Boom, I did that. Partial derivative of the vector value function que contain two parameters, two variables, u and b, and now differentiation with respect to b. Well, so now you consider u constant and differentiation with respect to b, and the derivative with respect to b, the first component is derivative cosine, es minus sine. Entonces es minus u sine b. The second component is sine, derivative sine is cosine, entonces u cosine. And this third component have no b, derivative 0. After that, when you compute the partial derivative, you apply cross product. Cosine b, sine b, 2u, minus u sine b, u cosine b, and 0. You know how you're doing that. So the answer of the cross product is a vector, of course, a vector is minus 2u squared cosine b, comma, minus 2u squared sine b, comma, u. And the magnitude of this vector, I know it's too long and complicated to say, therefore we can using software. Well, it's square root this guy, square root of square this guy, Es minus, pero become positive when you square 4u4 cosine square b plus what? Plus 4u4 sine square b plus u square. Well. I can see que 4u to the 4 power is common factor. I factor out. So we have cosine square b plus sine square b, que one. Disappear the b. The b is gone. So my big square root now is reduced like a 4u to the 4 power plus u square. And leave it like that? No, because we can factorization u square. And u square inside the square root, you put like a u outside. Actually it's absolute value, but it doesn't matter because the value for u in our problem is from 0 to 1, never is negative. So no, I don't care. According to this interval, it's totally unnecessary, not necessary. Put absolute value here. Entonces 4u square plus 1. Yes. Okay, entonces my ds. The surface area. No vectorial, no, because we have no, our function is 1. So this is typical surface integral per scalar. We don't need to compute flux. No. Is equal this. Let me copy the general formula. Ru cross Rb magnitude du dv. Entonces en our specific example is 4u square plus 1 u here du dv. Entonces now my surface area is the double integral of this integrand function du dv. And you see that we don't need Jacobian. Because Jacobian you apply, suppose under the consideration that you are doing an xy coordinate and you change to polar. Pero entonces in this case no, because automatically when you are doing this, so this is similar to Jacobian. In the lecture que hice yo, que es out the course, que es totally general knowledge to understand the big picture of the integration. This parameterization is similar. It's a change of variable. Actually, my original variable is bueno, no, in this case parameterization. The parameterization is equivalent to substitution somehow. Okay, and who is u? U vary from 0 to 1 and v vary from 0 to 1. Okay, yeah, of course we can separate because by curiosity, our integrand function depending only of u. Nice, I love it. And we have another integral here, que depending only of we have not in the integrand function. This part is obvious, que es 2 pi. And this part, let me see, it's no big deal. It's cal 1 or cal 2. We apply substitution, another substitution, no? Entonces you declare, for example, que 4 plus 1 is another variable, but normally I use u, but I have no u because I confuse a w. No, I put w, that's it, another auxiliary variable. And when you differentiate, this is au du equal dw. Okay, nice. Entonces, the differential is almost completed. We need only extra a here. So you put extra a here and you divide by a in order to doesn't affect my integral. Therefore, this is this guy and this guy together. This is dw. And we have a square root w dw. Wow, easy. And what about the limit? Well, the limit, no, wait a second. The limit is from 0, plugging in 0 here and u is 1. So 0 corresponding with the 1, and 1 corresponding with the 5, I suppose. Entonces, much better is 1 over 8 integral from 1 to 5 of the w1 half dw. Now you apply the power rule. The power rule say, okay, this is 1 over 8. It's a w increasing plus 1 is 3 half. 3 half divided by 3 half get the same multiplication to 2/3. And evaluate in between 1 and 5. Keep going here. Entonces es, bueno, okay. You can simplification a little bit here. This is divided by 2, 1, divided by 2 is 4, no? Entonces 12. Es 12. Es pi over 12. Pi over 12. Pi over 12. And you evaluate w, que w is 5. 5 raised to the 3 half. Leave it like that, que horrible. Minus 1. Okay. And that's it. No, don't forget to do pi, you know? What my final answer then? My final answer is multiplication. Wait. Hello, what the hell is that? Okay. This is 1, no pi. This is 1, no pi. You're right. This is 1, no pi. Where come from this pi? This is 1. In this integral, we have no pi. Now multiplication by 2 pi. So the final answer is 2 pi multiplication 1 over 12, paréntesis 5 raised to the 3 half minus 1. Entonces pi over 6 simplification, pi over 6, 5 3 half minus 1. Es el final answer. Okay, entonces the answer for that part is 12. You fix it in my paper. This is 12. However, bueno, so I suppose que es multiplication, right? Okay, no worry. Okay, super. Any question, guys? I try to do something in detail, no? And bueno, unfortunately, this cross product, no. I do but quickly. I did in my calculator, no? I get that. Any question? Do you understand very well the question number 10? Surface area. Okay, the question 11, 12, 13. Okay, all good. The question 11, 12, 13, and 14 is about the famous Stokes or divergent theorem. But you don't need to do it both ways. So you make a decision what way you consider better. Remember the Stokes theorem, so 11 questions. 11 questions say. Verify. Suppose the word verify say doing both way and verification. But no, because it's crazy. It's crazy. It's crazy. Some problem is crazy. No 11 and 12, but 13 and 14 is crazy because the vector field is horrible expression. No. So basically, we have a vector field. Is 0, negative z, y. And our famous surface is the intersection, one plane, and one cylinder. Okay, there's an hour. See, you need to understand, but you don't need to understand this. See, you want to understand the surface. We have, for example, here, like that, along this axis. And this is the plane. Okay, this is the famous plane. Okay, have intersect 1, 1, 1. 1, 1, 1. And the first quadrant look like a triangle, but no. When you are doing this plane, okay, this generate, I did in algebra, something like that. Okay, this is our surface. Es elixir, pero elixir en 3D. You can rotate in GeoGebra and you see, es elixir. Es elixir. So in my opinion, the best way to face that problem, so they want que you verify. Remember, let me recall Stuck theorem. Stuck. Stuck is a theorem that states the relationship between one line integral in the closed curve of the one vector field is given, dr. This curve, of course, is this curve. Okay, I suppose in the positive orientation is counterclockwise. And remember, si you assume que the surface, the normal vector of the surface is out like that. Let me try to do my best. Out, normal vector, too big. Okay, remember, when you're walking around the curve and your head point to the normal vector, your left arm touch the surface. Entonces, under this consideration, the surface integral is equal to the Stuck theorem is equal to the curve of f, similar to the green, but in this case surface, and the green is double. Entonces we have ds, no? ds. Dot product, and the ds is a vector. Okay, this is the idea. Entonces, I want to compute no in that way. No. It's possible, no? Pero no. I want to compute in that way. Okay. Entonces, where's my first job? Well, my first job is compute the curve. It's super easy. Compute the curve of the vector field. It's a famous determinant that you frequently see. This is symbolic, partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And PQR, who is PQR in our problem? 0 minus c and y. This is easy, so let's do it by hand. Remember the component I, the organization, component I, you delete this and this. Entonces, partial derivative de this is 1 minus partial derivative de this is 1. Es negative 1. Es negative 1. A negative 1 another negative become positive. Wow, it's 2i. Minus j. Minus j is this and this. Now, partial derivative of this with respect to x is 0. Partial derivative is 0. It's obvious 0. And k, okay, you delete this and this. Okay, stay this partial derivative with respect to x is 0, 0, is 0. So our curve is super easy. Is the vector 2, 0, 0. I like that because it's numerical. So maybe when you perform the dot product with ds, es just a number. Entonces es super easy. ¿O no? Hazlo. Okay, one way there are many ways. You find the parameterization maybe of the surface or no. Okay, or you, for example, you assume a normal vector. So you compute the normal vector. Okay, you compute the normal vector. Normal vector is, look. Normal vector or uninormal vector. See this guy. Who is this guy? Well, this guy is easy because the uninormal vector, remember how you find normal vector for the plane is the coefficiency, no? The coefficiency 1, 1, 1 in this case, 1, 1, 1. 1, 1, 1. Pero this is no uninormal vector. No. This is the normal vector, but no uninormal vector. The magnitude of this is radical 3, ¿no? Que es square root 1 square plus 1 square plus 1 square. This is uninormal vector. Okay, super. Entonces, when you try to set out the double integral, in which you simplify the surface integral now in double integral, well, I have no idea what is the region. No. Entonces, I try to do in the easy way. No parameterization. I can, pero no. I suppose que normally we are doing in the projection in the XY plane. Okay, entonces we are doing the parameterization using XY plane and maybe in explicit form. Entonces, bueno, okay. And inside the double integral, bueno, we have a vector, que es the curve, que es 2, 0, dot product. The normal vector, que es 1, 1, divided by radical 3. If you want, you put radical 3 inside, component by component, no? I need to finish with dx dy, or not necessarily dx dy. Remember the formula of the ds. A formula for the ds, pero ds, like a scalar, is in explicit is square root fx squared plus fy squared plus 1, dx dy. It's under the consideration que I'm projecting onto the xy plane. Entonces, pero, wait a second, what is the projection? Okay, this is a 3D problem. I want to do 2D problem. When you're projecting in 2D problem, I can see que the region R, remember, this is our surface is surface que lie on the plane x plus y plus equal 1, pero is bounded when enclosed by the cylinder. Therefore, when you're projecting onto the xy, you see cylinder, you see circle. Circle, and by the way, the radius 1. Wow, easy. Now, this is my region R. I suppose que I end in polar. I suppose. Okay, pero let me compute ds. Pero how you compute dx? It's easy. Bueno, dx, you compute the partial derivative f. Pero who is f? Well, f is this. Okay, f is this. The partial derivative with respect to the x. Okay. Okay. Let me try to do in detail. Look, this is my formula. X plus y plus c equal 1. I solve for c. C is equal 1 minus x minus y. This is totally in explicit form. And you know that this is f, x comma y. And when you compute a partial derivative with respect to x, it's negative 1. And when you compute a partial derivative y, it's negative 1. And when you plug it in here, my ds, the 1 squared is 1, negative 1 squared is 1, and we have another 1 dx dy. By the way, this is radical 3. It's no coincidence can happen. It's always happen, dx dy. And this radical 3 cancel. And your multiplication, dot product. 2 times 1, 2. 0 times 1, 0. So my double integral right now is 2 dx dy. Wow, too easy. Too easy, too easy, too easy, too easy, too easy. Entonces now, ¿es necesario o no doing in polar? What do you think? It's the region R. So my surface integral. Remember the beauty of this. We are doing the computation line integral. However, I convert using Stuck theorem to the surface integral. And this surface integral I manipulate in explicit E convert to a double integral. Okay. No, wait. Let's do in polar, no? Because the region is a circle, no? Entonces tú, dx dy es r dr d theta, no? Sorry, double. R vary from 0 to 1. And theta vary from 0 to 1. Okay, separate again to the theta is 0 to pi d theta. And the other guy is r dr from 0 to 1. This is 2 pi. And this is 1/2, no? Because it's r squared over 2, evaluating between 0 and 1. And this is 1/2. 1/2. That's 2 pi times 1/2, no? Okay. Don't forget 2 pi. Yeah. Entonces the answer is, I forgot 2 pi. No, I don't. 2 pi is this. Just 2. Okay, just 2. Yes, you're right. Okay, okay. Don't forget, o sea, don't forget these 2. Okay, here. It's one extra 2. Entonces es 4 pi. The answer is 2 pi. Yes. Okay, that one. The answer is then exactly I have in my paper 2 pi. You know, guys, we have too many details in this problem, no? Wow, too many details in this problem. Okay. Any question? What part is confusing? Number 12 is similar. Number 12 is similar. The application is you convert. This is very, very similar. However, let me see. I'm doing. Wait a sec. In my paper, I don't know why. Yes. Let's do it. Let's spend the time doing that. Okay, we continue in the question 11, but doing in my paper, I am doing no by the surface integral, sino I am doing by the line integral. This is just curious. No big deal. But in my opinion, the easy way is this, compared to the surface. Because look, when you compute the curve, the vector field is constant. It also was easy, relatively easy. However, I have in my paper the same version. Let me see, but it's the same. Wait a sec. Oh yes. Yes. Okay, let's do it. Curiosity. Let's doing. Okay, I want to erase everything, guy. I want to copy the part I like. Problem 11. This problem is too long. 11 problem. Okay. 11 problem. Remember the vector field was. The vector field was 0, minus c, y, no? And the curve, well, the curve is the intersection, something, o sea, the surface, sorry, no the curve, the surface is the intersection of the plane that plane and the curve. And we this look like a one elixir in 3D. Que my surface is this. Pero no, I did the surface part. I focus it now in the curve. Okay, I'm doing in that way. Integral in the closed curve of the curve C and the vector field F here. This is the way. Okay. So I need to parameterization the curve. I need to parameterization the curve. But it's easy. It's easy because I forgot here something. I forgot equal 1 here. Because the parameterization of the curve contain only one parameter, que es t. Normally they call t. Entonces x es cosine, radio 1, y es sine. Entonces es perfect value, x squared plus y squared equal 1. This equation is good. And c, no. C, si yo isolate c here, c is equal 1 minus x minus y, ¿no? Que es equal 1 minus cosine t minus sin t. Okay, entonces the parameterization vector value function for that curve is cosine t sin t 1 minus cosine t minus sin t. Okay, and this represents perfectly our famous curve. So you put in GeoGebra, remember in GeoGebra, no es surface, it's a curve. In GeoGebra you put curve, and you declare the component x, que es cosine, you declare the component y, que es sine, and you declare the component z, que es 1 minus cosine t minus sin t. You declare the only variable que you have only one, because it's curve, no surface. In surface you have two parameters, and the curve will have only one parameter because it's one dimension object, no? And t varies from 0 to pi because this is the totally closed surface. So the domain of this parameterization is from 0 to pi. T varies from 0 to pi. And this domain is one dimension, no? Suppose que dice t 0 to pi. Entonces, this allows us conversion, this line integral, and one easy integral like calculus. Okay, bueno, the rest is, when I need to compute dx, I need to compute dy, I need to compute dc. So we are doing line integral in 3D. But it's easy. Derivative cosine is minus sine. Derivative sine es cosine. Derivative z, que derivative 1 es 0. Entonces derivative cosine es minus sine, entonces sin t. Sin t dt, ¿no? And derivative sine es cosine, but we have a minus in the front, and cosine t. Wow. They put everything together. Okay, everything together means que I need to perform the dot product here. Who is f? Well, f is 0, minus c, y. Dot product, the famous dr vector que es dx dy dc. When you perform, we have 0, we have minus c, dy, no? Okay, this is 0, this is minus c dy, and this is plus y dc. Okay. Now I have everything in parametric way. Everything in parametric way. Entonces now I'm doing the integral from 0 to pi. I just copy. Who is z? Minus c. And minus c is this. This is c. Minus c is opposite sign. Entonces -1 plus cosine t plus sine t. This is c. dy. dy is cosine dt. Multiplication cosine t dt. Now let me see. Okay. Plus y. Who is y? Sine. Multiplication by dc, and this is dc. Dc is sine t. No paréntesis. Minus cosine t dt. Okay, let me try to manipulate a little bit. Okay, at least the algebra inside the integral. This is no big deal. Okay, this is minus cosine t dt, no? Okay, distributive property here. This is plus cosine square t dt. And this is plus sine t cosine t dt. And the second part is plus sine square t dt minus sine t cosine t dt. Entonces at least I can see que this and this is cancelled out as 0. You know, and cosine plus sine is 1. We have integral from 0 to pi of minus cosine t dt plus another integral from 0 to pi of dt, no? Because that part, cosine and sine together was 1, stay alive only dt. Okay. Es obvio que this integral is 0. And because antiderivative of cosine is minus sine, pero evaluate into pi is 0 and 0 is 0. And the only guy que stay alive is this. And the answer is 2 pi. Boom. Super. Very well. You see or no? What do you consider better? Solving by the line integral or solving by the surface integral? I suppose that both are complicated, right? However, I want to hear opinion. What do you think? It's better using line or using, you know, both are horrible, no? However, what is better? Carlos, Duque, what do you think? Line, Girardo line integral. Okay, it's up to you. It's up to you. And the test, you solve it in only one way. And when you have time and you want verification, and it's possible because sometimes it's horrible. Horrible gets impossible doing in both ways. For example, the number 13 and 14, no, this is crazy. Maybe 12 is pero it's crazy. Okay, any question, guy? Now let me see who is sleeping and who is aware. Chayir, are you there? Say yes or no. Or say something, no? Yes or no? No. Hadi, are you there? Answer me. Jocelyn, yeah, Yup. Brandon, Thomas. No, sleeping. Carlos Duque? Yes, sir. Ricardo? Present. Omar Borja? Omar Boja is sleeping. Daniela, no. Omar Boja, pay attention. Daniela Rabasa. 50. Edward. Yeah, Daniela, 50 is here. Daniela is sleeping. David Restrepo. Oh. Marco Morales. Marco Morales is also sleeping, ¿no? Ok, entonces hay detecting two sleeping. Marco Morales. Ok. Daniela is sleeping. Brandon Thomas is sleeping. 3 is sleeping. Wow. Okay. Okay, let's move on to the number 12. Let's see if we have time to do something or not. Number 12. Okay, number 12 is hard also. Complicated. Maybe we don't finish. Number 12 is another Stuck theorem problem. In which you verify to say we are doing both ways. In this case, doable in both ways. Vector field is square, comma x, comma c square. And the surface is similar. It's a plane y plus z equal to x squared plus y squared. This is similar. Good, very good. So you want to have some approximation of this surface in 3D. As similar, we have the cylinder, unicylinder here. And we have a plane. This plane is a plane que have missing one variable. O sea, ese plane alone the x-axis because it's missing. Entonces, ese plane que, bueno, I don't know exactly. It's 2, no? It look like that. This is 2. This is 1. This is one line. And the plane look like that. Something like that. And the surface, well, you can use a GeoGebra if you want to see in detail. Look like that. Okay, this is my curve, and this is my surface. Okay, the intersection, a plane, and the cylinder. Okay. Let's do it. Well, first of all, define orientation of the curve, orientation for the. Okay, look, the orientation. In my opinion, I'm walking in that direction. I'm walking counterclockwise. And the supposition that the orientation for the surface is like that. It's a normal vector. Entonces, when I'm walking around the curve, and my head going to the normal vector, my left arm touch the surface. Under this supposition, Stuck theorem said that the integral in the closed curve C f dot dr. Okay, I want to compare it that way now. So I need to find the parameterization of the curve using one parameter, no? Is equal the surface integral of the curve of f is a vector that this is another vector. Okay, let's do it in that way. For doing it that way, I need to focus in the parameterization for the curve. Well, I take advantage que es inscribed in the cylinder. Therefore, it's obvious que the equation is x equal cosine. Radio 1 again, nice. Y equals sine. But C no. C is, okay, I take this equation. Yeah, I solve C like a function of x and y, but we have no x, only y, 2 minus y. Good. Entonces es 2 minus something and y is sine. And this is my parameterization of the curve. Is vector value function cosine t, comma sine t, comma 2 minus sine t. Wow, easy. I suppose que t varies from 0 to pi. It's obvious because it's closed curve. Therefore, if you want to finish the line integral, well, you compute the x and dy and dz separately. And put together, because, well, because you can do the dot problem. Entonces es, okay. Derivative cosine is minus sine. Here I don't like that way because it's relatively systematic and easy. What is the disadvantage? The disadvantage is that the algebra in one moment become heavy, no? Entonces now you see, wow, make a mistake. Everyone may make a mistake, maybe. Derivative y que sine es cosine, t. And derivative z, bueno, es derivative 2 is 0, and derivative sine es cosine, but we have a minus in the front, entonces minus cosine t. Cosine t dt. Okay, entonces now, let's do it here quickly. The vector value function expressed in parameterization. Remember, my vector value function was, look, I come back at the beginning. Minus y squared. And who is y? Is sine. Entonces, minus sine squared. I try to write this vector field, pero plugging in the parameterization here inside. Component by component, no? Es the notation. Comma, x, pero x is cosine. Comma, c squared. C squared, look here I do the algebra crazy thing. Square. Dot product, dr, and dr is easy. Dr is the vector dx dy dz. Es minus sine t, comma, cosine t, comma, minus cosine t. dt. Okay, of course, integration here from 0 to pi. Wait. I hate that. I need to expand this. This is elementary algebra. However, you are inside the complicated problem of 3D. Entonces, in one moment, you have one algebra. It's no big deal. However, it's long. Entonces, it's exhausting doing that. Okay, this is expand that guy. F4 minus 4 sine t plus sine square. Make sense, guy? T is squared the first. I get 4 minus 2 times multiplication both plus square the second. Okay, good. Now perform the dot product. Dot product is multiplication component by component, no? First component and first component. Entonces, first component is this. Let me use in color to identification, si no I am lost. This and this together. Entonces es sine plus, because negative, positive, sine cubic, no? Sine cubic t. Okay. The second component is easy. Is cosine. Cosine, cosine square, no? Cosine square, yes, right. Cosine square. plus, wow, and this is hard because it's this times this. Entonces, minus 4, minus 4, minus 4, minus 4, cosine t. This is 4 and cosine multiplication. Plus 4, pero es plus, ya, porque es minus. Minus plus. Sin t, cosine t. Sin t, cosine t. Minus sine square t cosine t dt. Wow. Okay, we have a lot of things. However, I know que si yo integration trigonometric function in one entire period, que is 0 to pi, the only guy can stay alive. But I forgot something. I forgot the square here, right? Because cosine times cosine is cosine square. When you integration trigonometric function in one period, you know that the area under the curve of the function that are odd function is 0. However, the integration of the function que es even function is, bueno, no, like it's a square. Okay, entonces, using intuition, if you want verification one by one, then this integral is 0. This integral is 0. This integral is 0. And this integral is 0. And the only integral that stay alive is this. So it's integral from 0 to pi using symmetry, guys. Cosine square t. Entonces, one more time, I using the half angle, you know, formula cosine square t is equal 1 plus cosine 2t divided by 2, no? Or divided by 2 here and divided by 2 here, right? And this integral is 0 again by the same reason, because it's one period, and stay alive only 1/2 to pi. The answer is pi. Wow. The answer is pi. This is doing the problem of the point of view of the line integral. Do you see? I using, you know. Okay, if you want, you spend a lot of time. You take one by one integral and try to do separately, and you see the answer is 0. Make sense when it's odd function is 0, and when it's even, no. And you see, bueno, professor, cosine is not even, no, pero no square. And you know the cosine or negative cosine, either way, is something like that. And this is 0, and this is 2 pi, no? Okay, so this area is positive, and this area is negative. Entonces the positive and negative cancel out each other, right? Plus, and minus. That is the reason it's 0. And the multiplication sign cosine is also 0. And odd exponent is 0. Even exponent, no. Half angle, and you get that. Any question? Okay, let's try. Let's try to do using surface. So that we compute the left-hand side of the Stuck theorem. Now I move into the right-hand side. Maybe I don't know if it's easier or more complicated. I don't know. I have no idea. Hirado don't like surface integral. Hirado don't like surface integral. Okay. I respect that. Depende, no? Depende del example. Okay. Yeah, depending the example. I want to do in both ways to illustrate. In the real life, so you need to compute that. Okay, guys, in the real life, you don't need to compute anything. Because in the subject, you apply these mathematical tools. Maybe you compute something, but not too much. So the basic idea is to understand the physical meaning of this new integral, line integral, double integral que you see in fluid mechanics or in electromagnetism. Okay, you see double integral. So you don't know, for example, line integral. You don't know what is the line integral. You believe que the line integral is the same integral que you take in Cal 1. No. It's along the line. And surface is over surface. It's completely different consideration, right? And so I propose you stop here. Stop here. And we continue doing the half part of 12, 13, and 14 next time. Okay? And next time maybe you finish early and we start doing the lecture that I would like to explain of the big picture of the multidimensional calculus and a little bit of the electromagnetism. Okay, super, no problema. Everything okay? Let me stop.